Okay, here's where we're at in our robot training. This is a cobot arm in our virtual workshop, sorting some small hardware, nuts, bolts, and, well, not washers just yet. Here you can see that it sorts large nuts and bolts quite reasonably, however small flat objects are quite painful. A key feature of this setup is that the working surface is not actually solid, it's soft. You can see here in this grab that the fingers are able to press into the surface to get a grip further down on the part. A flat washer lying face down on a hard table, it's a well-known problem in general, and especially tricky with these grippers. The go-to solution to this would be to just use a suction-based solution. It's very difficult for the gripper to pick up any small variance that you would find in reality, and the jaws are just going to close on it and it's going to slide out or flip out, or you'll just push it around. You won't ever pick it up. The idea is pretty simple. It's based on having a part that's on a soft surface, and the idea is to press down on one side of the washer in this case, and then come in with the other finger and gently lift up the washer into a position that's vertical but still with some distance down from the top of the washer so it can be grabbed and lifted properly. And the rest of the video is about how we've built the model, and we're training on the model for that. The first surprise is that making a soft pad is actually quite generally difficult to simulate as well. NVIDIA has a material called FEM material. I went down a rabbit hole there. We won't go into it here. But right now we're going to use what, if I'm pronouncing it correctly, what's called a Winkler Pasternak foundation. It's basically like a mattress. It's a bunch of small units which are all spring loaded, and then those spring loaded parts are all connected to each other. So it basically is a grid of squares that all influence each other, and you have a number of parameters that you need to control in order to form the material. If there's not enough influence between the parts, then the material tends to behave a bit more like a gel or something. Like you press down and it just cuts directly into the material, with creating steep cliffs. Trying to lift from that creates the washer to flip all over the place. If you create too much influence between the materials, then it starts to become more like a hard surface again, or just one great big spring that presses down and forms like a plate or a curve. So you have to play with the parameters, and what I've gone for here is a neoprene type material, like basically what a mouse pad might be made of. Then the next step is to train the gripper to find angles and distances down to press, use sensors that you might model in the gripper, and then lift up the piece. And that's just a set of parameters. So how far over the rim to press towards the edge, how deep you're going to press, where the other finger begins, when to start closing it after the press, how high to lift, which way the finger goes towards the other finger, which one moves, which one stays in the same relative position. All these are parameters that you train for. And then you can see here that we use Isaac Lab to create a whole population of tests. The view is much bigger than this, but I'm just showing a few. And then, each one of those tests performs the maneuver with a slightly varying set of parameters, and then you find the best ones, and then you iterate on those and create even more parameters. And you also have to be careful about what you're rewarding as well. At first I was rewarding just simply the ability to pick the part up, or the distance with which it can lift the part, and then you would get a population of tests that flip the part up. Instead of gently lifting it, it would press down and then flick the piece up to vertical, and that works, but it's quite unstable. So sometimes it flips up vertical and sometimes it throws the part right out of the area, and you don't really want to train for that. You want a part that you press down, it lifts it up at a gentle angle, and then you can lift it up. And if you fail at that, then the part's still there and you can try again. Whereas if you're putting a lot of energy on the part and you flick it out of the arena, you can't try again in reality. You can obviously try again in simulation because you just put it back to its starting position, but then you're training against something that is really good in simulation and not so good in reality, or not so stable in reality. Anyway, here you can see the culmination of all the efforts. A lot of training went into this, a lot of iterations, a lot of watching videos, because it's the only good way sometimes to see that it's working, whereas use a agent like Claude, and it will say, yeah, it's working, and then you watch the video and it's flipped the part, or the part's disappeared completely. So you have to watch the videos. But anyway, you see here, it presses down, it bends the piece up, and then it gently lifts them into place, and then it lifts the piece off the pad. So that's where we're at. The next step will be to put this into the workshop scene, so you can see it getting picked up and sorted with the other parts. I haven't done that yet. This Isaac Sim project here that I showed you earlier, I've got a lot of other features to develop on there, and it consumes most of my local GPU, while the soft surface work that I've been doing is more like a development spike. It's a side quest that I'm working on in parallel, just to be able to pick up more parts in the demos that I've been doing. And because my GPU is always consumed on this Isaac Sim project, then I don't actually have any bandwidth on my own computer to do this work. So what I actually do is I deploy it to the cloud. For that, I'm using a Nebius, which have what's called a serverless job. So it's not really a traditional virtual machine. It's more like just a script that you can run on your computer and then send all of this off to the cloud. I mean, first I test it on my computer, and then once it's past its basic smoke tests, you run the major training in the cloud and then pay by the hour. And that works pretty well, and that's allowed me to do more than one job at a time when I've only got one decent computer at home for doing this kind of heavy-duty GPU work. And not only that, having much more powerful GPUs at hand has allowed me to take it to the next level. A lot of these early tests that you can see here is just 9 or so parameters being controlled to do a pickup in simulation. The next level is to take it to 50, 60,000 parameters using a machine learning loop. And I'm doing the early work on that right now using the Nebius cloud servers. This is what you would call one step before a full reality simulation. You're reading the sensor data, but you're also reading the position of the part in simulation at something like 20 hertz. So you can tell exactly where it is instead of having to use visual recognition or something to predict where it is. And then from there you train on different materials with different randomizations. And not only that, I'm adding the ability for the model to change materials, because as I said at the start, we're training towards a neoprene material, but it might be that that's not the most optimal material to select. So you can in fact train on finding different materials, and in the end a soft polyurethane material is where it's currently predicting to be the best kind of surface to pick up a flat object from. But it's all a work in progress, and it's nice to have some powerful servers at hand that I can just spin up on demand for that. And that's about all for today. Thanks for listening.